Hello, so in this video we're gonna look further into acceleration, velocity, displacement, all that stuff. And what we're gonna do is start to work out some equations to actually start working these things out, right? So last time we looked at graphs, the plot things, so for example to plot the displacement or the velocity as someone goes through a journey, right? But we didn't explicitly work those out. We were given them. We just had to draw the graph to represent the various velocities or displacements, right? So we're gonna start working out some formulas for this stuff, right? And I'll say as well, this is where it actually becomes mechanics at this point. We looked at some boring stuff, some basic stuff so far. But now this is where mechanics, I'd say, really begins. But anyway, so let me paint the scenario. So what we're going to basically be looking at throughout the remainder of this chapter is we're going to look at, say if someone is at one point A, and then they are at the point B, right? Some time between A and B, right? So they travelled some distance, X meters. And initially, at point A, they are walking or moving forward with an initial velocity u, so u meters per second. Okay. Then at point B, they now have a velocity, a speed of v meters per second. Okay. All throughout the journey, they're accelerating at a meters per second, right? So that's the acceleration, okay? And obviously they travelled at time t seconds to get from point A to point B. So that's the scenario we're going to look at. So we've got a distance between 2 points. We've got the initial velocity and the final velocity from one point to another, the acceleration throughout and the time throughout, okay? So these 5 ingredients, if you will, so the acceleration, the final and initial velocity, so the starting velocity at point A and the final velocity at point B, and the distance throughout, okay? We're going to be working with this. So that's the scenario we'll be working with. So from one point to another, we're going to be looking at the displacement, the velocities, and the acceleration and the time, okay? Right, so I mentioned we're going to start looking at formulas to work these things out, right? Okay, so cast our minds back to a velocity time graph, which we looked at last time, where we have time in seconds and our velocity in meters per second. Now, what I'm going to propose is we start the graph at a velocity of u, okay, not at 0 but at u, okay, some velocity u, and then it travels with constant acceleration, meaning it's a straight line, okay, and then we finalize our journey, so we're at the final velocity of v, okay. So this is the starting point and this is the end point, and at the end point we're at time t. Okay, so it's pretty generic, right? Pretty generic. So again, initially, I have the initial velocity u, and at the end I have the final velocity v. Okay, and this is in t seconds. Okay, right. Now I mentioned the acceleration is just a, right? Well, actually, when we looked at velocity graphs last time, we said that the acceleration is basically the gradient, right? And the gradient, well, what would be the gradient here? Well, firstly, the change in time, which is t, and the change in velocity. Now, the change in velocity is v, this gap here, v take away u, right? So therefore, the gradient is the change in velocity, which is v minus u over t. But hang on, this is equal to the acceleration. So we can say that the acceleration, which is just a, A is V minus U over T. And there we are. We got our first formula. So what we can do here is we can work out the acceleration given the final and initial velocity v and u and the time. Or we could work out something else, right? If we were given the acceleration instead, we could work out one of the other things if we needed to find that out, okay? But this is one equation we can gather. Now, what else do we know about velocity time graphs? What else do we know? We know the area underneath them represents the displacement, right? Or the distance, right? But the displacement here because it's positive. Okay, so if I was to again draw this line here, and then have this, and then we can spot. I have a trapezium, right? If I sort of if I draw this out without the graph, right? Hopefully you can spot I've got a trapezium shape, right? These are my parallel sides. This is my two bases, right? Now, and so the height would be here. Okay, that's my height. And these are my two bases. So I need, if I was to work out the area of this trapezium, which would be the area under the graph, I need to work out what these three sides are. So firstly, this side. This length is up to u, right? What's this side going to be? That side is going to be v plus u, right? So I have u here, and then v plus u, and then the base. Well, the base is just t, right? Then there we are. I've got all my ingredients here to work out the area of this trapezium, which will give me my displacement, right? So, the area then, the area under the graph, that's the area of the trapezium that the graph makes, which is what I've drawn here, this trapezium shape here. Well, firstly, again, the base and the top, the parallel sides, are u and v plus u. So it's going to be half of v at u plus v plus u times the height of the trapezium, which is here, t. Okay. So if we sort of work with this, then we have a half t, right? A half times t. Lots of u plus v plus u is 2u plus v. If we expand this out, we get, well, a half times 2 is 1, so it's just ut. Then I have a half t times v, that's going to be a half vt. Okay. And there we are. So we can't do anything more with that. But we know the area under the graph, that's equal to the displacement. So that means the displacement is equal to this expression here. There we are. Now the final thing to note is with displacement, because everything else is in letters, u is the initial velocity, t is the time, and v is the final velocity. A was also the acceleration. We need a letter to represent the displacement. We call that s, okay? So s is equal to ut plus a half vt squared. No, half vt, sorry. And that is my second formula, okay? So these two formulas we can work out from the velocity time graph in this way, okay? And so these formulas give me ways to work out various stuff like the acceleration, the displacement, the time, the velocities, right? So that is it, right? So what we'll be using for the rest of this section and in later on as well are these formulas here. Okay, these are called SUVAT equations as well. Why SUVAT? And this is in capital letters. It's an acronym. Well, not an acronym, but S stands for the displacement. U stands for the initial velocity. V is for final velocity. A is acceleration, and T is time. And so, if I make a list here, the SUVAT, if I was to write down what I just said. S is the displacement. Now that's going to be in meters. U is the initial velocity. That's going to be meters per second. V is the final velocity in meters per second as well. A is going to be the acceleration. That's going to be in meters per second. And T is time in seconds. Okay. So we can work with these 5 quantities here and use the 2 equations we just worked out to work out these things, right? So as a reminder, we had V is U plus AT and S is UT plus a half VT, sorry. These 2 are the formulas we'll be working with in this video. So before we look at examples and applying this, there are 2 things to note. These formulas here, these formulas or formulae only work when the acceleration is constant. Hence, why this topic is called constant acceleration, because the things we'll be working with only work when the acceleration is constant, which means if we go back to our example here, the acceleration of the person walking from point A to point B, the acceleration is always the same. Acceleration will be fixed, okay? The reason for that is that we got these formulas from the velocity graph, but in order for we need to make sure that that we have a straight line, right? So the gradient, the acceleration, the gradient is fixed. It's always the same, okay? So that allows us to find the formulas, okay? The other thing to note is, as well as acceleration being constant, is you need to pay attention to your units, okay? So when we looked at SI units in the previous chapter, again, we need to make sure that our units are in SI units. The units matter. We can only use the formulas work when the units are in meters, or SI units, right? The SI units. So that means it's in meters per second, meters per second, which is the acceleration, and time in seconds. Okay, so if you got kilometers, for example, you're going to need to convert the kilometers into meters, or hours, you need to convert hours to seconds before you use these formulas. Okay, so let's have a look at some examples with this in action. Right, and one more thing to note, you'll be very glad to know, these formulas are in the formula book. Okay, we will be looking at more formulas in the next video, but you do not need to remember them. But when you use them more and more, you probably pick them up anyway, but they're in the formula book. Okay, so in this example, we are told a cyclist is travelling along a straight road. She accelerates at a constant rate from a velocity of 4 to a velocity of 7.5 in 40 seconds. So find the distance she travels. So firstly, pretty much what you're always going to want to do is just plot the information and do like a very rough sort of drawing to illustrate what to put the information down. So we're on a straight road, okay, so she accelerates at constant rate, so again it's constant acceleration, which is key, from a velocity of 4. So initially she has 4 meters per second velocity, and then the velocity after that is 7.5, right? So then 7.5 meters per second at the end here. Okay, so we start at 4 meters per second and end at 7.5 meters per second, okay? And the time is in 40 seconds. So I'll say that the time is 40 seconds, okay? Right, so what we have is the initial velocity, the final velocity, and the time between the two parts of the journey, right? So in part A, we want to find the distance. So what we're going to do with these sort of questions, again, you can have your own method, how you lay it out, but how I would do it is, obviously we've got SUVAT. So S is for displacement or the distance. So S, we actually want to find that out. So I'm going to put question mark, right? That's what I want to work out. U, so SUVAT U is the initial velocity, which is 4. V, which is the final velocity, which is 7.5. And A, which is the acceleration. I don't know it and I don't really care at this point, so I'm just exit. And T is the time, which is 40. Okay, so what we have is we want to find the displacement S. We've got U, V and T. If we then stare at our two formulas, which one do we want? So which one, basically, to work out which formula you want to use, which one does not include A? Because we don't care about A. It's this formula here, right? S is a half of U plus V times T. Okay, that formula there. Right, so at that point, we just substitute the information in. So the displacement S is a half of U, which is 4, add V, which is 7.5, times T, which is 40. And at that point, that's just a calculator job. So if we put that in the calculator, we get 230. So that is the displacement, okay? Or in this case, the distance. Okay, so the distance they travelled is 230 meters. Okay, right, then in part B they want the acceleration in the 40 seconds. So in part B, now we're dealing with acceleration. So S, well, we do know it's 230, right? We work that out. U is still 4, V is still 7.5, A, the acceleration, question mark, because I do want to work that out, and T, which is 4. Okay, and so I ask myself, what formulas can I use? Which one has A in it? I guess. If I only got these two formulas to work with for now. So the only one that includes A is this one here. So I can find acceleration using V is U plus 80. Okay, so if I state that formula now, if I sub my values in, V is 7.5. That's going to be U, which is 4, add A, which is just A. I want to work out what A is, acceleration. And T is 4. No, 40, sorry, 40, not 4. 40. So then this is just an equation to solve for A. So if I do 7.5 take away 4, that's going to be 3.5 equals 40 lots of A. Then A is simply then 3.5 divided by 40, which is 7/80 as a fraction, and that would be in meters per second. Okay, that's my acceleration then. Okay, right, so that's the idea, right? Fairly straightforward example, but that's the main idea, right? We work with the information given, we do a very rough plot of the stuff we're given, and then we use the formulas to work out any missing stuff that we need. Okay, right, let's have a look at this question. Okay, there's a lot of parts to this one. So a particle moves in a straight line from a point A to a point B with constant deceleration 1.5 meters per second. The velocity at A is 8 and the velocity at B is 2. So again, let's plot the information sort of given, right? So we have a line, it's on the line. So this is the point A, let's say, and at A, the velocity is 8. Okay, so at point A, the velocity is 8. And then we have a point B at the end here, and the velocity is 2. Okay, so 2 meters per second meters per second. Sorry, and okay, that's my initial and final velocity at A and B. We're also given acceleration. Now they said constant deceleration. What that means is deceleration, you should remember, is negative acceleration. Okay? So that means in this direction, the acceleration, and I'm going to denote that with a double arrow. Okay, so you notice with velocity, it's a single arrow. Acceleration, I will represent that with a double arrow. So that's going to be not 2 meters per second. No, so 1.5. Not 1.5 for acceleration, but negative 1.5. Because again, deceleration is negative. That means it's slowing down. Okay, it's slowing down because the velocity is going from 8 to 2. Okay, and that'd be meters per second. Okay, so I'll plot the information, that's all I'm given. Then in part A, it wants me to find the time taken from A to B. So I want the time. So again, if I list my SUVAT, my S, my distance, displacement, I don't care about, I'm not given anything. U is the initial velocity of 8. V is the final at 2. A is the acceleration, which is negative 1.5. And T is the time which I want to work out, right? So then I ask myself, because I don't care about S, right, the displacement, which formula does not include S? Well, again, it's V plus U plus, V is U plus AT. So if I make a note of that, there we are. So I want to find T. So if I sub my values in, then V, which is 2, is going to be U, which is 8, plus AT, so it's going to be minus 1.5 lots of T. So then I solve for T. So if I do 2 take away 8, I get minus 6 is minus 1.5 T. Therefore T is going to be minus 6 over minus 1.5. And that will be 4. Okay, so T is 4. Okay, and that being seconds. So there we are. That's the time taken. Then in part B, it wants to find the distance. Okay, so the distance. So now that's going to be S. So what's the distance? U, which is again 8. V is again 2. A is again minus 1.5. And T we worked out to be 4. Okay. So, I need the formula with S in. So it's going to be this second formula here. S is a half of U plus V times T. And again, I know what U, V and T are. So S is going to be a half of 8 plus 2 times 4, and so that's a calculator job. So the displacement is, and by the way, that is an S, not a 5, an S. I don't know how to make it clear, but there we are. That is S displacement. So a half of 8 plus 2 times 4 is 20. So 20 meters there. That's the distance. Right, then we're given something else. So then we're told after reaching B, the particle continues to move along a straight line with constant deceleration 1.5. So the same acceleration minus 1.5. The particle is at the point C, 6 seconds after passing through A. Okay, so what's happening now is it's reached the point C. So if I extend the line, we're at a point C now. And again, the acceleration continues to be minus 1.5. And we're also given the time, okay? So the time from A to C is 6. Okay, so I'll make a note of that. The time from A to C equals 6, okay? Now, what they want here is to find the velocity of the particle at C. By the way, this particle, you'll see all the time in mechanics, and you think, oh, what the hell is a particle? To be honest, for mechanics, we say basically everything's a particle. So it just means an object. It could be probably anything. It could be a person, could be a car, could be anything really. And when we looked at the modelling assumption is a particle is basically just a single point that doesn't really have any air resistance, basically. Nothing really too major, but it's just an object, okay? It's just a weird way we describe objects. Anyway, so the velocity of this object, this particle. So what we're given, well, again, the acceleration is still minus 1.5. So let's list, all right? Let's list our SUVAT. So S. Now think about it. So we want the velocity at C. So if I call this velocity V now, meters per second, that's the velocity at C. So let's think about it. If we want to start from A to C now, right? So the initial velocity is 8, okay? So U is 8. Now S, the distance, we don't know the distance from A to C, right? We know the distance from A to B, we worked that out in part B, is 20, right? That's 20 metres. But we don't know the distance from B to C, so we don't know from A to C either then, right? So S is out the question. U is 8. V, well, V is what we want to work out, right? What's the velocity at C? What's the final velocity at C? Okay. Then A is the acceleration, which is again minus 1.5, and T is 6, because we were again told the time from A to C is 6 seconds. Now actually we have enough information to work out V, because we know U, A and T. So again, we can use V is U plus AT here to work this out. So V is U plus AT. So therefore V is going to be 8 minus 1.5 lots of 6. And then if I work that out, that's just minus 1. So minus 1 meters per second. Okay. There we are. And it's negative. It's negative here. Which basically means at C, it's starting to move backwards. Okay. So if it's negative 1 meters per second here. So remember, with velocity, the direction matters. So if it's negative in the forwards direction, that means it would be positive 1. It'd be positive 1 in the backwards direction. So it'd be moving backwards at that point at speed of 1. But we can still include that. We can still include negative 1 that way. Okay, so the distance from A to C. Okay, that's what I'm getting at then. The distance from A to C. So again, if we consider the overall distance then from A to C. Well, again, let's use our SUVAT. So at D, part D, we know that S, that's the distance we want to work out. U is going to be again 8. V was minus 1. A is minus 1.5, and T is 6. Okay, so right. So that's from A to C, right? So the initial velocity of A, the final velocity of minus 1, and the acceleration and time there. So again, if I want to find Sn, I can use this formula here. So a half of U plus Vt. Okay, so Sn is going to be a half of 8 plus minus 1 times T of 6. So if I work that out, I get 21 meters there. Okay. I must admit as well, this negative V is bugging me. That is right. But usually, I guess we want to specify positive values for speed or velocity. So again, as I said, this minus 1 here, what we can say is if forwards is a positive direction and it's negative, we can just flip it and say it's 1. So what we can say to specify this and make it more clear is we can say, or the speed is 1 meters per second backwards. Okay. So we do give a positive answer. We do give a positive speed, but then we specify the direction. I don't know. I don't like leaving the negative velocity, but there we are. Okay, so that's that. Okay, so we've got this question here. So example here, so we've got a car moves from traffic lights along a straight road with constant acceleration. The car starts from rest at traffic lights and 30 seconds later the car passes a speed trap where it's registered as travelling at 45 kilometers per hour. Find the acceleration. Okay, so again, let's plot the information we're given. So we have this road, and initially we're at traffic lights here, and then here we're at the speed trap. Okay, we're at the trap here, we're at the lights here. Okay, so The car starts at rest. Now at rest means it's still. So there is zero speed or velocity there. Then 30 seconds later, so the time t is 30. 30 seconds later, the car passes the speed trap at the end here, where it's at 45 kilometers per hour. Okay, and we need to work out the acceleration. Okay, so again, S for distance, displacement, we know nothing about and we don't care about it. U is 0. V, the final velocity, is 40. I'm not going to leave that there, right? Hopefully you can spot the issue. It should look quite weird at this velocity because of the units. And A, the acceleration, is what we want to work out. And T is the time of 30, okay? Now, this velocity, why can I not just write 45? Because the units are kilometres per hour. Remember when I said at the start, we need to consider SI units before working with these formulas. And kilometres per hour is a problem. The velocity or speed should be in metres per second, like this. So, cast your minds back to when we looked at converting units. So firstly, we need to convert 45 kilometres per hour, right? So I'm going to convert 45 kilometres per hour into meters per second. Okay. Now, remember when we did this? So if we want to convert 45 kilometres per hour, but firstly, let's just deal with kilometres per hour. That's kilometres over hours, right? Because remember, h to the minus 1, anything to the minus 1 is just a flipped fraction. So we're dividing by h, okay? Now, we want to convert this into metres per second, like this. Metres over seconds. So what we're going to do, again, 1 kilometre over 1 hour. Now, it's not going to be 1 metre over 1 second, because what we're going to do is we're going to convert them individually. So firstly, the kilometre. 1 kilometre, you should recall, is 1,000 metres. So there we are. That's the top bit. 1 hour is actually going to be 3,600 seconds. Now, if you're not sure about that, remember that 1 hour is 60 minutes. And also remember that 60 seconds is 1 minute. So therefore, to get 1 hour in seconds, we do 60. In every minute there's 60 seconds. So 60 minutes, we do 60 times 60, which is 3,600 seconds. Okay. Hence, 1 hour is 3,600 seconds. This is my sort of conversion factor. So then if I just simplify the fraction, 1,000 divided by 3,600 is 5 over 18 metres per second. So what I can do here to convert 45 lots of kilometres per hour, that's going to be 45 times 5 over 18, which is sort of a conversion factor. And that being then in metres per second. If I just work that out, I get 12.5 meters per second. There we are. So that is the velocity I want to use, 12.5. Okay. Now, okay. So again, I don't want the formula with S in, so I want to find A. So I'm going to use V is U plus 80. Okay. So then V, I know V is 12.5 thanks to my conversion. And U is 0. A is, well, A, because that's the acceleration I want to work out. And T is 30. So, at that point, we just solve for A. So, 12.5 is 30A. Therefore, A is 12.5 over 30, which is 5 over 12 meters per second. Okay, and I can add that onto my diagram if I want to. So the acceleration with a double arrow is 5 over 12 meters per second. Okay, then in part B, what's the distance? So this distance here in meters. Okay, so what's that distance going to be? Well, again, if we use SUVAT here, S, I want to work out what S is. U is 0, V is 12.5, A we worked out to be 5 over 12 and t is 30. Okay, so then the formula with s in is going to be this one. I'm going to want to use this. So s is going to be a half of u plus v times t. So therefore s is going to be a half times u of 0 add v of 12.5 times t. So times 30. If I put that in a calculator, that's going to be 187.5 meters. That will be the distance between the lights and the trap there. Okay, and there we are. By the way, you don't necessarily okay, so we've got this question here, and we're told a cyclist travels with constant acceleration x from rest to 5 meters per second in 20 seconds. She then decelerates from 5 meters per second to rest with constant deceleration a half x. We need to find x. Okay, so again, let's just kind of just jot down the information we're given. So again, it's on some sort of road, right? Some sort of surface, some line, right? So initially, let's say here, she starts from rest. Now at rest means they're completely still. They're stationary, they're not moving. So there's no or zero velocity. Okay. And then she goes from 0 to 5 meters per second. Let's say here. In 20 seconds. So here. And then the time here. Oh. The time here is 20 seconds. The time is 20. Okay, and we're also told at this point she travels with constant acceleration of x. So acceleration, I'm going to again represent with this double arrow line of x meters per second. Okay, then we're told after she reaches 5 meters per second, she then decelerates from 5 meters per second to rest. So actually this continues on, and then at the end it goes back to rest. So she returns back to 0 meters per second at this last point here. And then at this point the acceleration here at this part, the sort of the journey, it's a deceleration again. So if the acceleration is a half of x, because it's decelerating, it has to be negative a half x meters per second. Okay. So I think that's all the information we're given. Okay. So we want to find the value of x. So I know the time specifically for this first half of the journey, right? So let's work with that. Let's just consider that. So I'm going to take therefore I'm going to take the initial velocity to be 0. So firstly, s, I don't know anything about the displacement or the distance, and I don't care about it. The final velocity, the initial velocity is 0. V is 5. The final, a, the acceleration is x, and t is 20. So actually I have enough information to work out x, okay, the acceleration. So again, I want the formula because I don't care about s. So I'm going to want to use this formula that doesn't have s in. So v is u plus 80. So therefore v is 5 is going to be 0 for u, add x lots of 20. So then if I solve for x, I get 5 is 20x. So therefore x is 5 over 20, which would be a quarter or 0.25 meters per second. Okay, so there we are, that's x. And then I can sort of add that onto my diagram, because if the acceleration is x, that means it's now 0.25. 0.25 meters per second. And also this bit here, if it's minus a half x, that's going to be minus a half times 0.25, which is minus 0.125. So I can add that on as well. I can adjust that. to minus 0.125. There we are. Okay, then it wants the total distance you travelled. Right, so as we sort of discussed, this journey is kind of in two different parts, right? So we've got this half here, right? This half, and then we got this half after, okay? So what I can do is, well, if the total distance you travelled is going to be from the start here to the very end here. If I was to just work out the distance, literally from here to here, the major problem I have if I was to use SUVAT is the acceleration is different in these two parts. It's 0.25 then minus 0.125. Remember, the key idea when, as we looked at previously, the key idea when using these formulas, you can see it here, even in the formula book, has to be constant acceleration throughout. If I'm starting to get different accelerations, I can't use the formulas in that way. So what I need to do is essentially split it into two parts, right? So if I split the distance to this part here, I'll call that x meters, and then this part y meters. Now I've solved the problem, because this part, this first half, the acceleration is just 0.25, and then in the second part, the acceleration is just the same at minus 0.125. So I'm just going to apply it in these two. I'm going to find the distance separately and then add them at the end. Okay, so again, let's focus on this first half of the journey. So firstly, if I use SUVAT, so S is my distance, that's x. U, okay, so if I look up here, U is the initial at 0. V is 5. And the time, well actually I'm given the, no, the acceleration is 0.25. And the time we're also given, time is 20. Okay. Now, okay, so now I can use the formula with S in, which is going to be this formula here. So a half of U plus VT. So if I sub my values in, S is going to be a half of 0 plus 5 lots times 20, and that would be, no, that's X, okay, so that would be 50. So that tells me X is 50 meters here, okay. There we are. Okay, now I'm going to do the same for Y. So this second half of the journey, here. So here, so I'm going to split this up and say the first part, and now the second part. Okay, just to make it clear. So at this point, S is now Y, the distance Y. U, now U, in the second half of the journey, the initial velocity is now 5, right? And the final velocity, right, goes back to 0, okay? And then A, as we discussed, the acceleration is minus 0.125. And then the time T, well, I'm not given the time here. I'm not given the time, right? So I don't know it and I don't care. So if I was to then jump to my formula for the formula for displacement here, S is going to be, or Y, and that S is a half of U plus VT. And so therefore Y for S, the distance is going to be a half of 5 at 0, or just 5, or times T. So that's going to be, Y is half of 5. That's going to be 5 over 2 lots of T. Well, the problem here is I do need T. Okay, I do need T. Now, actually, in the next section, there is another formula where we don't need T. We can just work it out at this point, but we've got to work with what we got. Okay, so we need to find T, the time. We can do that. We can do that because we can use the other formula to work out T. So V is U plus AT. So if I call TT, then V is U plus AT. So then I know that V is 0, U is 5, and A is minus 0.125 lots of T. Now I can get T that way. So then minus 5, if I move 5 to the other side, it's going to be minus 0.125 T. Therefore T is going to be minus 5 divided by minus 0.125. That would be 40. Okay, 40. So now I can add that on. Time is 40 seconds in the second part here. So now I can sub T into here. So now T is going to be 5 over 2 times 40. And so therefore Y, so 5 over 2 times 40 is now 100 meters. And so then the second part of the journey, right? The distance here is 100. So the total distance is then 50 at 100, right? So the two parts combined to get the whole journey. So if we add that, which is 150 meters. And there we are. Cool. So it's not uncommon where you might need to split up a certain journey to different parts like that, okay? But there we are. Okay, so I've got this question here. Right, so we're told here a particle is moving with constant acceleration in a straight line. It passes through 3 points A, B and C with velocities 20, 30 and 45. Okay, so I'm just going to plot it, okay? I'm not going to read the rest of that out. So if I plot the information, right, again, we have points A, B and C here. And at the velocity at A is 20. The velocity at B is 30. And at C is 45. Okay, I'm also told the time taken to move from A to B, so it's going to be this time here, the time from A to B is T1 seconds, so T1. And the time taken from B to C, the time is T2. Okay, show that T1 over T2 is 2/3. Okay, right. Bye. So, okay, right. So we need to show this sort of fraction here. So how on earth am I gonna get that? Well, again, notice it's kind of split up into two different parts. We've got a different time here and a different time here. Again, maybe I can sort of consider maybe splitting them up individually. Okay, so if I do that then, so if I do from A to B, firstly, my distance, I don't know anything about, I don't care about it. U, well, it's 20. V is 30 if it goes from A to B. A, well, I don't know it, but I might need it. But I'll leave it there for now. T is T1. Now Now I'm going to need either displacement or acceleration, right? I'm going to need either. Okay, well, what I am told is it's constant acceleration. That's really all I'm told. But it's the same acceleration throughout, right? If it's moving with constant acceleration, it says it's basically saying it's the same acceleration all throughout. So if I just say it's A, right? If I just call it A meters per second, then A meters per second, okay? So between the two journeys, it's still A. The acceleration is still A, okay? So if I just call that A then, what formula can I use? I can use V is U plus AT, right? Okay, and so there we are. So, V is 30, so 30 is going to be 20, add 80. And you'll see why I picked A and not tried to find S. You'll see why in a moment. Okay, so if I do AT, that's going to be 30 take away 20, which is 10. Now I'm going to leave that there. Now, then if I consider from B to C, so now I'm working with this, this part of the journey. That's from 30 to 45 meters per second. So if I do SUVAT again, S again I don't care about. U is, well, 30 and then 45 for V. A is still A because it's the same constant acceleration, and T is T2. Okay, T2 here. So that should be T1. Okay, it should be T1 up here. So AT1 is there. Okay, now you'll see why I picked A here, because it's the same value. A is A in both equations. You'll notice I get a sort of simultaneous equation in a minute. So again, I'm going to use the same formula. V is U plus AT. It's the only one without S in. So therefore V is 45. It's going to be 30. Add AT2. So if I take away 30, I'll get AT2 is 15. Wow, I've got two equations, right? Now A is the same. That's why I went for acceleration and not tried to find distance, because the distance will probably be different, right? The distance will probably be most likely be different in the two parts of the journeys, so it wouldn't tell me much, really, sadly. But because the acceleration is the same, I can sort of it will help with solving the equations. You'll see in a second. So I've got these two equations, right? I've got AT1. AT1 is 10 and AT2 is 15. So I need to show this equation here. So T1 over T2 is 2/3, okay? So actually, if I even just if I then just say here AT2 is 15 in the bottom, it might actually be just by moving the equation down, it might be apparent what we can do. So if I want to show that T1 over T2 was, what was it, 2/3, right? That's what I want to show, right? I want to show this. So if I'm starting here, these two equations, it's hinting I want to divide T1 by T2. So if I call this the first and the second equation, if I want to divide the first one by the second one, right? Because then I would have AT1 divided by AT2. So that I get the T1 divided by T2, which is 10 over 15. Okay? Because if it equals 10 and equals 15, so then we divide them. Okay, and then the A cancels. Again, that is why we wanted to work with the acceleration. Because if it's the same in both parts, they cancel like this. And very nicely, we T1 over T2, wow, 10 over 15 is 2/3. There we are. Okay, we got there. Cool. Okay, now we are told the total time to move from A to C, so the total of the two parts is 50 seconds. Right, so if I then say that overall, I have to squeeze it in here, that the two times is 50 seconds, right? So that means if it's 50 seconds overall for the two parts, then T1 add T2 has to equal 50, right? So if I note that down, so T1 and T2 is 50, but also we have T1 over T2 is 2/3 from part A, right? Anyway, so they want to find the distance from A to B, okay? But we come they want just this distance here. I'll call X meters, right? In fact, I'll do it here. So they want this distance here. Cool. Right. So before we jump to that, we're probably going to need to solve for T1 and T2, because T1 in particular, that's the time. what's it called? That's the time for this first part of the journey here. So we want the distance x between A and B, but also going to want the time between A and B, because the distance formula requires the time. So we're going to need to find T1 here. So if we deal with these equations, we're going to just need to solve them like simultaneous equations. Okay, so firstly, let's just deal with this fraction one. So if we cross multiply, so T1, T2 in this way, so 3T1 is 2T2, right? So then T1, if I divide by 3, is 2/3 T2. I can then sort of substitute that into this equation here. Okay, so I sub T1 into the equation T1 add T2 is 50. So therefore, I have 2/3 T2 add T2 is 50. Well, 2/3 T2 add 1 T2, right? That's 5/3 T2, right? If I'm just collecting like terms, okay? So therefore T2 is going to be 50 divided by 5/3. If I say put that in the calculator, I get 30. So T2 is 30. Cool. Then I can say that therefore, if T2 is 30, using this sort of equation here, T1 is going to be 2/3 of T2, so 2/3 of 30, which means that T1 is going to be 20, right? 20. So there we are. So I can fill that in. So T1 is now, if I look at my diagram, so T1 is 20 and T2 is 30. So T2 is 30 here, T1 is 20 here. Okay, now I can start to work out this distance x between A and B, right? So, okay, so if I start to do my SUVAT, so from A to B again, my SUVAT is S is x, that's the distance from A to B I want to find. U, so if I go back to my diagram, U would be 20 and V would be 30 between A and B. A, the acceleration, we still don't know what A is. We could find it, but we don't know what it is. But T is, well, T is T1, which is 20, right? So again, as we just saw, the time from A to B is now 20. Okay, that was T1. Right, so actually, I don't care about A, but anyway, so again, what formula can I use? With S in, I can use this formula here. So a half of U plus VT. So S is a half U plus VT. So X for S, so X is going to be a half of 20 add 30 times 20. And you can see why I needed to find the time, because again, the distance formula requires time. Anyway, so if I do a half of 20 add 30 times 20, I get 500. And that is my distance from A to B. And there we are. Cool. Okay, so we've got some exam questions on this. So, we are told a train travels along a straight track between two stations A and B. And then, okay, we're just giving some information, right? So, again, like usual, let's just jot the information down. I'm not going to read it all out in one. Okay, so firstly, okay, so if we were to just plot the information down. Okay, so we are told the train starts from rest. So again, if it's at rest, that means the speed is 0. Okay. And I'll say that's A, right? At station A, then it ends at station B. Okay. Then it moves with constant acceleration 0.3. Okay. So the acceleration is 0.3 meters per second. Okay. Okay, then we're told the train moves at constant velocity. Okay, so then it reaches some velocity. Let's say, I don't know, v meters per second. That'd be somewhere in between. Then we're told it moves with constant deceleration. Okay, so then after it moves with deceleration of 0.5, so it's going to be negative 0.5 acceleration, right? And then it comes to rest at B. Okay, so that's the situation we've got. And also we're given that the time when it goes from 0 to then this velocity v, which is constant velocity, the time was 80 seconds, was it? Yes. So this point is 80 seconds. Okay, so what they want is to work out the value of the constant velocity here. Okay, so again, we have, so if we work with this sort of first half of the journey, if you will, this first part here, we can see that, so the first part, that's going to be the S. I don't know anything about distance, I just don't care. U is 0. And the velocity is V. The final velocity here is V. The acceleration is 0.3. And T, the time is 80. So therefore we can find this velocity V. Again, if we look at our formula, we know that V is U plus 80. That's the formula without S in. So therefore V is U plus 80. So velocity V is 0 add 0.3 lots of 80, which would be 24 meters per second. Okay, so there we are. So that is the constant velocity of 24 then, right? That's part 1. Then the second part, we need to state the time for which the train is decelerating. Okay, so in this second part here, when it's decelerating, okay, which is negative acceleration again. So we need to find this time here. Now we know the initial velocity is 24, right? And we know the final 0. So again, for this second part here, again we can use SUVAT. So the final part, the second part, again the distance I don't care about, I don't know. U is 24 now. That's the initial speed here. V is 0. Okay, at the end here, 0. A, the acceleration is going to be negative 0.5. Again, as a remind you, negative acceleration does not mean the speed is negative, it just means it's slowing down. Okay, so anyway, so minus 0.5, and T is what we want to work out. So again, V is U plus 80, so therefore now V is 0, it's going to be 24 minus 0.5 lots of T. So then we can solve for T. So then therefore minus 24 is minus 0.5 T. So then T is going to be minus 24 divided by minus 0.5. And so that would be 48 seconds. Okay, so I can add on here. So time is 48. Okay, cool. Then it says for the third part to sketch the velocity time graph. Okay, so this is back to what we looked at previously. So again, a velocity time graph looks like this. So we have time in seconds, velocity in meters per second. Right, so let's have a look at this situation again if we were to plot this information. So the train starts from rest and then moves with constant acceleration for 80 seconds. But as we saw, it then ends up to 24 meters per second. So I'm going to say up to 24 meters per second. So we can add that on. So the first part of the graph needs to go from 0 velocity to 24. Okay. So 24 there. And the time the time was 80 seconds, right? So 80 here. Right, the second part of the journey is the train moves with constant velocity. It doesn't specify how long for. So remember, constant velocity then just flat lines at the same speed of 24. Again, I don't know what time that is, I'll just call that T. Then it moves with constant deceleration, so it's going to go down, okay? And it goes from 24 then to 0, okay? So it's going to go down from 24 to 0 as it decelerates. And I know the time that takes to decelerate, we'll work that out. The time is 48, so I can add that onto my diagram. Well, the time it takes, it wouldn't be 48 here, but the time it takes is 48. So this width here is 48, okay? And that's really all I can add, to be honest. There we are. That's my graph. Then it says in part B that the total distance between the two stations is 4,800 meters. Okay. Right. So using the model, find the total time taken from A to B. So in other words, if we look at our graph, at the very start here to the very end. So if the distance is, what was it? 4,800 meters, that's going to correspond to the area under the graph, right? So the whole area under this graph has to be 4,800. So okay, so that so if I say then that this is 80, right, 80 seconds, then this is time t, and then we've got 48 seconds at the end. Okay, hopefully spot I got a trapezium here, right? I've got a trapezium. I've done many examples with working out the area with a velocity graph last time. So again, I've got these two sides, so it's my sort of parallel sides of the trapezium, my top and bottom. So firstly, the total time, that's actually what I want to work out actually. That's what I want to work out, the total time. But actually, if I know the first part is 80 seconds, then t seconds when it maintains constant velocity, then a further 48 seconds when it decelerates. If I add all these together, the total time is just going to be 80 add t add 48. And then 80 add 48 is 128. So 128 add t. And that's my bottom side. And then the top side up here, that's just going to be t. Right, and then my height is just 24, right? So now I can start to work out the area under the graph. That's the area under a trapezium, which is going to be half of the two bottom top sides. So 128 add t, add another t, because that's the top side, right? Add another t, times by the height of 24. So now we sort of simplify it. So if we simplify it, that's a half of 128 add 2t times 24. Then if we do 24 times a half, or 24 divided by 2, that's 12 lots of 128 add 2t. Then if we expand, we get, well, 12 times 128 is, okay, 1536 add 24t. And there we are. And again, the area, as we're told, the area has to be 4,800. So if we equate this to 4,800, we can solve for t, okay? So then 24t is going to be 4,800. Take away this 1536, that'll leave me with 3264. So therefore t is 3264 divided by 24, and that would be 136. And there we are. But that's not the total time, that's just t. That's this length here, t. The total time is 128 add t. Okay. So 128 add t, that's going to be 128 add 136, which would be 264 seconds. And that is my answer. Okay, there we are. It can be quite a confusing question, but that it's a sort of nice question. It brings everything together that we've done so far in a way. Anyway, the last part of the question, it says, suggest one improvement that could be made to the model of the motion of the train to make it more realistic. Again, I went over this in one of the questions last time. The main criticism with this sort of with what we're working with is constant acceleration. That's the key thing that holds us back. Okay. And in reality, I discussed this last time. In reality, things don't always move at the same amount, at the same rate. Okay, so things don't move at the same constant acceleration. They don't move at the constant speed for large periods of time. They constantly fluctuate. There might not be large fluctuations, like we might move from say 30 miles per hour to 31 miles per hour, but they still fluctuate pretty much all the time, right? But what we're working with, sort of these equations don't account for that. Okay, they don't account for natural, realistic fluctuations that would affect the motion. Okay, so that is the limitation. So the improvement is we need to account for variable movement, so variable acceleration, to make it realistic, to make the model realistic. We should account for variable acceleration. Okay. Okay. There we are. And I'm going to say throughout the whole journey. Okay. Because technically we do have different accelerations, but they're not many different. So here, what was it? We had 0.3 meters per second. Then it goes to 0.5 meters per second. They are technically different, but there's only two different accelerations throughout the whole journey. I'm talking fluctuations like every second, that sort of thing. So we need, I guess, more variables, more variable acceleration, more specifically. Okay, so that's that then.